We've spent a lot of time following a humble bell crank through the digital thread, but now I want to take a step back and look at the big picture and really begin to investigate the value of the digital thread. To do that, I'm going to talk to Deloitte's Joe Sheeby and to Aaron Johns, the U.S. Navy Technical Account Manager at Siemens PLM Software. Guys, I have been all over the country chasing this digital thread. A lot of moving parts, lots of words on this screen. Can you give me the big picture and put it all together for me so that I can understand it, holistically?
Absolutely. So one thing we learned is that depending who you are and what your day-to-day role is, you view the digital thread as something completely different than what you and I would view the digital thread. So if I happen to work in CAD/CAM, I may see that as really the only area where I need to concern myself with the digital thread. Or if I'm in non-destructive examination or inspection, that may be my only real purview into
I'm a guy who that's what I look at.
That's my digital thread to me. But I think what you and I see as a digital thread, it's connecting all these different disciplines, all these different pieces of information in one single strand of data across the life cycle of a program or an asset.
Okay, so Joe, draw a picture for me.
Sure. Yeah, so a lot of words on the screen. What we like to do is just jump into a simple graphic of how to visualize this. So this is our standard digital thread graphic across 4 distinct phases to help internalize what this looks like. So we have scan, design, and analyze, build and monitor, test and validate, and deliver and manage.
Okay.
And so scan, design, and analyze are some of those upfront steps that you saw during your journey.
Yeah, so we started with, we got a bell crank, right?
Mm-hmm.
We've all seen this before. So we started with a part that looks a lot like this that exists on an airplane today, and then we ended up with this topology optimized part. That's all.
Exactly. Yep, so that's the upfront. There's some design work there, but also the computer-aided engineering work to look at, what are our inputs into that topology optimization to look at how we improve the design the next iteration.
Okay.
So both the design and the analysis step. And coming out of that first phase, what we have is really a as-designed model of our part that we're going to produce.
Okay, so I know what I want.
You know what you want.
That's the design.
You have the specifications of how you're going to get there. That's the as-designed model. And the idea is that you package those outputs in a usable way and send it off to a machine operator to actually manufacture a physical part.
Okay.
So to go from digital to physical.
Okay, and this is where all the in situ monitoring that we did,
Exactly.
Watching the thing be built, that's all in this notion
capturing
of
post-processing activities. All that information is gathered here, and all of that data is packaged into what we consider to be an as-manufactured model of the part.
Okay, so I have as designed and as manufactured.
Exactly.
Okay.
And so those two pieces.
So I know what I wanted and I know what I got.
Exactly.
Right? Okay.
The whole idea there is that in the test and validate step, a testing technician wants to compare that as manufactured model against our as designed model to see whether or not we can field the part. Does it meet its performance requirements?
Okay, so I might have a standard inspection protocol that everything gets, but by comparing those two things together, I'm going to get a smart inspection protocol in some cases that's going to say, no, look at this particular thing.
Exactly, ways to save time and money in terms of what techniques or technologies you might use to inspect the part.
Okay.
Yep. And then not just that, but once you actually field the part, how can you continue to learn from your part as it's out in the field? So via performance data that's collected, usage data that's collected, how can we understand those performance conditions that the part's being subjected to and help it inform an even better design in the future? And so we call that an as-maintained model of the part.
Oh, okay.
So you actually keep a live digital representation of that physical part in that landing gear assembly as our example.
Okay, so I got as designed, I got as manufactured, and I got as maintained.
Yep.
Okay, so two other concepts that I've heard quite a bit about. One is this notion of this body of knowledge, and then the other is this notion of feedback. What's the story there?
Yeah, so throughout the process, in each of those individual steps, like we talked about in terms of simulations and the machine instructions, you're collecting, these icons show just the body of knowledge that's flowing through the process. And so at every single phase, there's more knowledge that's being collected.
I've got them all the way, going all the way
and they're all the way down.
Yeah.
And so you're collecting that information because you want to reuse it. So if we know how to successfully print this part, as our example with the bell crank, we can use those same specifications as we go about printing it again and again and again, and save on the time that it takes to do this again.
Okay.
So squeezing it from weeks to days to be able to get there.
Feedback.
Yep, and in the feedback part, there's many different feedback mechanisms throughout, but the most notable one that I think has a lot of value to it is capturing this performance and usage data over here on the far right and getting that all the way back into design. So we can understand the actual loads that bell crank is experiencing in the landing gear assembly.
Yep.
We know if it's greater or less than what we expected it to be. And we can improve upon our simulations to keep producing better and better parts as we gather more and more data. And that's one of the big benefits of that feedback loop.
That's interesting. Aaron, so Joe showed me the high-level picture. You showed me a word cloud before that. How do all those pieces fit into this picture that Joe showed me?
Well, sure. So really, if you look, this is another way to look at those four phases of the digital thread as we defined it. But what's the infrastructure needed to maintain that digital thread?
Yep.
And really, the first piece is product lifecycle management, and our product is called Team Center.
Okay.
But what product lifecycle management allows you to do, it's much more than just managing information about a part. It's about managing information about a part. It evolves over time, but also it's interrelations to systems and subsystems of whatever your product is that you're trying to design.
Okay, so all those pieces, all those words that you had, that we started with, are really kind of become the boxes that slot into each of these areas, and they're all feeding in, whether it's as designed, as manufactured, as maintained or sustained, driving into this PLM, product lifecycle management system, where this body of knowledge is living and growing. Is that right?
Precisely, but not in a vacuum. So each one of those pieces or elements of data needs to drive other elements of data and other pieces of the life cycle. So you have that interconnectivity all the way through the digital thread. So I can take data from my computer aided design, which I can use to drive my motion simulation, which I think you saw some of.
Yep.
But then I can use that to drive my finite element model. I can take those loads and use cases, use those forward in FEA. I can use those forward in topology optimization, because I know from a simulation standpoint what loads this part needs to undergo in the field.
So far, we've spoken to designers, technicians, and strategists about the benefits of the digital thread. But what does an actual CEO think? To find out, I took a flight with Alan Klappmeyer, the CEO of One Aviation.
One of the unique things about aviation that makes that whole digital trail so critical is that for airplanes, both from a safety point of view and from a regulatory point of view, we keep track of everything. From the initial ideas, through the design, through the analysis, through the substantiation, the testing, through the manufacturing and the incoming sourcing, quality control, every bit of it is kept track of. By having better control over that information, you make the base requirement easier to accomplish. And then you begin to leverage that use of data. This is such a game-changing concept in aviation. It sounds overstated, but in fact, I have a hard time imagining how you could ever have done it without the new technology that we have available.